Hello, check, check, 1, 2, 3, hello.
Hi, Afzal.
Hello, Shreyas, how are you? By the way, we are live on YouTube.
Oh, huh.
Hi, how's it going?
I just wanted to. Good. How are you?
Yeah, I'm fine as well. Just a second. My new text.
Hello, Shreyas, how are you?
Just a second. Okay, now it's good. Actually, yeah, I'm using YouTube as well, just so that I can see the live chat. So it was that audio. Anyways, how are you?
That's good.
How are you?
I'm good. Yeah, I just wanted to help with the testing, but I think you have it covered already.
I have checked the YouTube. I think it's okay. For people who are watching on YouTube, can you tell me if there is any issue with the sound? Okay, it will take 20 seconds to go to YouTube. So there's a delay. Anyways, yeah, I'm really excited, actually. I'm a big fan of Howard Stone, so it's going to be fun.
I know.
Yeah. Let's see. Yeah, and he wanted it. Oh wow, he wanted it to be interactive. So, oh, they've started a machine in the background, which sucks, but it's okay.
Yep.
I hope they stop in 10 minutes or 15 minutes, but let's see.
Yep. Yeah, I'm just moving into my bedroom. It's surprising that you don't hear it on a loop because the YouTube sound should go through the Zoom again.
Yeah, but there is a.
That's true.
Hey, Tyler. Tyler's here as well. How's it going, Tyler? Can you hear us? Hey guys, I'll be back in like 5 minutes. Okay. I'm going to go and tell the person to wait for a while. Let's see.
Sounds good.
Hey, Tyler. Hey, Shresh. Thank you for joining early. Let me make you both co-host in case something goes south.
Yeah.
How are you, Tyler?
I'm good.
Co-host. Nice. Thank you for joining early. I just asked him to stop before 2, but let's see. Yeah, I mean, they were not there literally 5-10 minutes ago, and it didn't happen.
Yeah.
Yeah. Anyways. So you're in Austin, Tyler? Are you in Austin?
Yeah, I'm in Austin.
Nice.
Got back a few weeks ago after I helped my parents move.
Nice.
I got my wisdom teeth removed, so I haven't really done anything the past week.
Oh yeah, of course.
Couldn't eat Thanksgiving dinner.
Oh, that sucks.
Yeah, I've been eating soup. I've eaten so much tomato soup in the past week.
Tomato soup. Yeah, that's good. I've been cooking for a while after the exam. I am, just killing time. It's end of the semester, and I mean, I took Omar's course, so that's something. That's killing some of the time in this conference. But yeah, I'm killing time with cooking. It's a nice stress buster. Didn't go anywhere for Thanksgiving. Like, did any of you travel?
I'm already in India.
Oh yeah, of course.
I went to San Antonio, but
okay,
that's it's a 75-minute drive. It's not far.
Yeah. I'm hoping that this Omicron variant doesn't spread too much, and I didn't go home during summer vacations because of this variant, because things were so uncertain. But let's see.
Yeah, sort of gambled.
I mean, I don't care. I'll be going home in January. There's whatever happens, we will go. It's a tough situation. Yeah, it's a tough situation, I must say. I mean, I don't like to stay away from home for that long, but I mean, no one likes that, of course.
Yeah.
So where are you from, Tyler, by the way? And this is all live streaming. So if there's someone who has a crush on Tyler, will know,
I'm from Cincinnati.
I'm
from Cincinnati.
Okay.
So I've got a flight back there in December.
Nice.
December through January, something.
That's awesome.
Sorry, what state is that?
Ohio.
Okay, yeah.
Nice.
So yeah, but I'm depending on how much the variant spreads in the US in the next few weeks, I might drive home. Because the flight was cheap anyway. So, but it's a really long drive, so I kind of don't want to do that.
Anyways, how's everything else? How's research? We're doing PhD, right? Are you TAing any class next semester, Tyler?
Nah, I'm not going to TA.
Okay. Yeah, I mean, I would like to do TA, but it's just killing your research time. So I'm holding back. until
exactly.
there is a funding crunch, and there will be after, I would say, 1 or 2 years, there will be funding crunch. Then I have to, I think, TA a few courses.
Yeah,
let's see.
I partially TA'd. I wanted to TA. I mean, I feel like I've gotten like more TA experience than most people in our program anyway. So, but at this point, but it was partially because that way, after my fellowship ran out, I'd have more leverage in terms of keeping less of a salary drop, because Bjorn didn't have to pay for a few of those semesters with TA.
Nice.
At least I don't think. I think that the CSEM TAs comes from a different source, but I'm not sure.
Yeah, it does.
Do you recommend TAing?
TAing the CSEM courses isn't too bad. Feliciano's is a bit more work, I'd say.
Yeah.
Just because, granted, this last year wasn't that bad, last spring semester, because a lot of people deferred. Because I know when I was TAing your guys' class, you, Shreyas, and Evan, there was like 20 some papers to grade each time, but there were only like 12 last year. So it was like, it was a lot less work grading.
Yeah. You know what? I really miss Feliciano's class. And I'm wondering if there is any quantum computing class here at UT.
Yeah, there is.
I want to, there is in CS.
Scott Aronson. One of my roommates is advised by Scott Aronson. So
Scott Aronson is like probably like the most famous quantum computing expert in the world.
Yeah, he's got like he's got a blog. But yeah, he teaches a quantum computing class here, I'm pretty sure.
Okay. I'll look into that.
One of his students was in the news a couple of years ago. She was 18, and at the time there was a algorithm that had been developed that they believed was polynomial time on quantum computers and non-polynomial time on classical computers. And she was in the news because she developed a polynomial time version of the algorithm on classical computers. And she was literally 18 at the time, which was insane. And I think a senior in undergrad at the time. And that was my first time hearing about Scott Aronson or UT really. So pretty impressive introduction.
Definitely. Interesting. So how are you, Evan?
I'm okay. I got a cold over Thanksgiving that I'm still getting over. I've been sick now twice in the last month, which has not been great. But I think a lot of people are getting sick because nobody has immune systems after 2 years of not seeing other people. So like you can literally walk around campus and hear people sniffling. It's kind of funny. They're like coughing.
Oh, interesting.
You look great. I like the beard, man. It seems like you've really been growing it out.
Oh yes, of course. I am growing a beard. One of the hobbies I've developed recently. So
that counts as
let's see how long.
Okay. Yeah. No, I mean it's still looking great. You're killing it, whatever you're doing with it. So I think you can go bigger. We'll see.
I will. Let's see. I will. I'll go to the breaking point, but let's see.
Yeah. How does the wife feel about the beard? Is she a fan or not so much?
She likes the beard. Actually, she's on the call. So.
Oh, nice. Nice to meet you. Officer's wife.
I like beard, and I like changes. I mean, you can either get clean shaved. You can have a haircut like Evan. Evan is very nice with haircuts, and I like changes, and seems like it's a good change. You have to find something which looks good.
I can certainly relate.
I just shave my hair off because it's easier.
Yeah, that was part of my inspiration, I guess. But I was just like, it'll be cheap and easy, but
yeah, in
Well-
undergrad, my hair was pretty much cut like Evan's all the time because I bought like a $15 thing and I would just cut my own hair.
yeah.
Oh.
I am realizing though, like, wow, it's gonna be like a year and a half until I have like
I get you.
reasonably length
Yeah,
hair.
exactly.
Like,
Yeah, it's awesome.
well, yeah, but yeah, it's awesome in terms of convenience. I didn't quite think through the long-term ramifications of the decision. As fun as it is to go like this, at some point I think I'll miss having hair.
It
Don't you
feels
like
good
the-
though when you if
Yeah,
you
don't you
touch
like the
it,
wind
and,
on
you
your
know,
scalp?
Yeah, exactly.
Yeah,
That's-
yeah. It is nice. I did discover I have a little bump on the top of my head though. Not ideal. But now I know never to shave my head. You know, that one it looks so good. So that's nice.
Interesting.
William.
Okay, people are joining.
Nice.
Let's see.
Yeah, nice to see you, William. Or
Yeah.
not actually see you, but see your name. Yeah.
Hi,
Do you know what
William,
time?
Jonathan.
Do you know what time
Oh.
Dr. Stone is hopping on?
Yes, he asked, like, he told me that he will be joining 5 minutes earlier for testing, but
Okay.
let's see. Yeah, but let's see. And yeah, we actually received response from outside UT as well. So there will be people who are not a part of UT on this call.
Okay,
And,
great.
we have verified their identity, so it shouldn't be a problem.
Yeah, I'm sure it won't be.
Yeah.
Do you have everything set up with the YouTube stream and any issues?
Yes.
Okay, everything's great. Okay.
Yes,
Do
I
you- do
tested
you-
the sound. Mhm.
Do you need somebody to monitor the YouTube comments?
I mean, I have my iPad with me, so
Oh,
you know,
perfect.
I'm like-
Perfect. Yeah, well prepared.
watching the comments,
great.
and
Just wanted to
so
make sure.
those who are watching on YouTube, feel free to comment, and I will ask. Okay, Professor Stone is here.
Yeah.
He prefers to be called Howard. So let's see. Hello, Howard. Can you hear us?
Can you hear me?
Yes.
Yeah, no one ever, I don't think I ever got a Zoom link, so I was just searching for it.
Okay, I actually sent you multiple times. I'm not
Oh,
sure
you did?
why.
Then I
Yeah.
just failed to find it. I was searching through all my emails.
Okay.
How are you doing?
How are
Sorry
you,
about
Howard? Oh,
that.
no
I'm
worries.
hanging in there.
Nice. I
How's
see the
Evan?
mask. Seems like you're in the office.
Just teaching
Oh, no,
on
it's-
campus. We have I don't know about you guys. We are masked indoors. Well,
Yeah,
at least
that's
when there are other people around. So
Yeah, that's the recommendation here as well. Although, because it's Texas,
yeah,
nothing can be enforced.
here it's a requirement. So, which I think most of us are pretty happy with. So, let's see what do I have to do here. I have to find my talk. So, Evan, are you on the faculty, or you're a grad student or postdoc?
I am also a graduate student. Like Afsal, I'm a third-year student in the Odin Institute.
So
and-
Asal, you didn't tell me. I thought you were a postdoc. You're a grad student?
Yes, I am a grad student. I just ended my candidacy. I'm in my third year
Oh,
at
great.
Odin Institute for Computational Engineering and Sciences.
And what do you work on?
So I work with Mark on two-phase flow in a viscosity
Oh, Mark Hess.
compacting
That's
matrix.
how I
Yes.
met you maybe a
Exactly.
couple of months ago.
Exactly. That's
Yeah,
how
you
we
guys
met.
are making me work pretty hard here, by the way. But it's,
I hope it's fruitful. I mean,
well, we'll find out. Only one way to find out.
of course. Let me make you the co-host, and I think then you'll be able to share your screen. But I would like to introduce first. When the time comes, I feel like
Yeah,
right now
I
we have.
much prefer very short introductions, nothing dramatic.
Okay, sure. I will keep that in mind. And yeah, I mean, we have we can wait till 2:05, and before that, I think it would be nice if we can introduce ourselves, if we can.
Sure, I'd love to
switch on our
hear from everyone and see. Can I see? Let's see. How do I see a gallery view? I see. I got it.
Yes.
Cool.
So if someone would like to introduce themselves, feel free, and just go ahead.
Yeah, so I already mentioned that I'm a third year
And what
student.
do you work on?
I work on problems in computational imaging. A variety of different approaches, including I've been focusing on the experimental design aspect of computational imaging, specifically with aspects and applications in MRI recently.
Great.
Which has been very, very cool. And Tyler's on the call as well. Tyler's, I believe, a fifth year student in the SIAM program.
Yeah, I'm a fifth year student and I'm working on optimal transport for seismic source inversion.
Very, very nice. So most of these are, you're both looking at the applied mathematics side of it, or trying to get more information from the images, or what exactly? Like in the MRI question.
Yeah, so not to get too in the weeds, but in an MR imaging experiment, a subject is placed in this strong external magnetic field, and these magnetic pulses are applied. And these magnetic pulses can be parameterized by the time between the pulses, how much they rotate, the net magnetization, etc. And so we can consider the problem of optimizing these parameters in terms of minimizing the Cramér lower bound of the unknown parameters in the subject's tissue that we're hoping to estimate at the end of the day. So that's how the problem can be formulated. And I've been working on various approaches that build on that, including some optimal control types perspectives.
Right. Given the number of people on the call, maybe we run through a bit more of the people. How about that? I met Evan and Tyler. That was good.
Yes. So the stage is open. Anyone, if they can, unmute themselves and, if possible, switch on their screen and introduce themselves. I think that would be awesome. Right now it's 2. I think most of them will be here by 2:05. So I think for next 5 minutes also we can have a small chit chat and then get started. How about that, Professor?
I think it's great. And I told you yesterday
perfect.
You should call me Howard. That's okay.
Oh, my bad. Sorry. Okay. So yeah, if anyone would like to, introduce themselves, now is the perfect time.
Not to put you on the spot, Shreyas, but Shreyas is actually the VP of SIAM at ET. If you want to unmute and say hi.
Oh, hey Howard. Sorry, I was away from my screen for a couple of minutes. I'm also a third year PhD student at the Odin Institute. And my advisor is on the call as well. So I'm working with Patrick on an inverse problem in computational glaciology.
Computational what?
Glaciology. So
great.
ice sheets.
Yeah, great. Important problem. Is the inverse problem well posed, by the way?
No.
So we have Professor Arbogast as well on the call. Professor Arbogast, would you want to, introduce yourself if you haven't met? Professor Arbogast is our faculty advisor for SIAM. So Professor Arbogast.
Hi, it's great that you can give this talk, Howard, and we're looking forward to it.
Afzal twisted my arm a lot, so I'm a little sore right now, but it's okay.
Okay, so the idea which we had when starting this distinguished speaker seminar was, we have all these department seminars and people go there, but there are other topics as well, such as this one, which I think is very important to be discussed among students and among early career researchers. So I think, considering your experience, we would definitely, at the end of the talk, we would definitely come up and learn something. And that's one of the reasons why we started this seminar series. And so like, since, this is not a very well-defined path, we are still learning on this. So that's why, it took a while to converge to some sort of talk title and, things which can be discussed. And since this is going to be an interactive session, I'm really looking forward to it.
Yeah, I'm going to try, and there are a few places where it can become interactive. I would like that if it happens, but that's going to require the participation of the audience. So
Definitely. So we have Shin with us. She's the treasurer for SIAM. Shin, would you like to introduce yourself?
Hello, everyone. Nice to meet you. My name is Shin Tang, and I'm a second-year PhD student in Older Institute. My background is in chemical engineering and computational science. So I'm actually working with a chemical engineering professor, Michael Baldia, and we're working on optimizations of power grid and energy storage. And maybe in the future we will also work a little bit for optimization of like chemical process, stuff like that. But it's also,
I mean, the power grid, it's an important question and sort of extra important in Texas, given what happened last year.
yeah, definitely.
So
So, have you contacted our dean about this talk?
who's your dean? Are you talking to me or
Roger
someone else?
Bonacase, maybe you met him?
Oh, no, Roger Bonacase. I forgot he was your dean. Roger sent me a note this morning. He and I were office mates in graduate school.
I know, that's why.
No, he sent me a note this morning. So, no,
So,
Roger.
but he's not here. As long as he knows, that's good. Yeah.
No, I haven't seen him in a long time, but I first met him, I don't know, almost not quite 30 years ago. So, no, oh, sorry, not quite 40 years ago. So,
All right.
long time ago. Time flies.
Interesting. So we have Professor Odin here and Mark.
Professor
on the
Odin's
call.
online. I didn't see.
Yeah, it's just a lot of people.
I'd love to say
That's
hello.
awesome.
Oh, hello. It's a little dark where he is.
Yeah, Professor Odin, you're on mute if you're saying something.
Okay, Howard, who said truth is beauty, beauty is truth? That is all on earth there is to know, and that's all you need to know.
You're asking me who said that?
Yeah, your title has beauty in it. Beauty is truth. It's a famous statement by Keats.
Okay, I'm going to give you the quote from someone else who's not Keats, but who's a scientist. So
Keats.
they might disagree. They might agree on truth is beauty, but they might disagree on what constitutes beauty.
Well, some agree on what constitutes truth too. Okay, thank you for being here.
Oh no, it's great, and I'll have to look up the quotes from Keats. I'm not as erudite or broad as I should be.
Okay, I think we can get started now. Good afternoon and hello, everyone. I welcome you all to the third Distinguished Speaker Seminar organized by the Society for Industrial and Applied Mathematics chapter here at the University of Texas at Austin. I'm Mohammad Afzal Shadab, the president of the chapter, and it is my great pleasure and honor to introduce you to one of the greatest fluid dynamicists of our times, Professor Howard Stone. Howard is a chair of the Department of Mechanical and Aerospace Engineering at Princeton. He did his PhD from Caltech in 1988, and he worked at Harvard and eventually became a Vicky Joseph Professor of Engineering before moving to Princeton in 2009. He has received several prizes.
Afzal.
Yeah.
That's okay.
Okay, perfect. So today, he's going to talk about something special. As students, we often study courses and apply concepts to solve real-world problems. Research in itself is a beautiful journey which requires creativity, hard work, and perseverance. Most importantly, it requires the love and passion for an idea as a learner, explorer, and a communicator. Today, Professor Howard Stone will share his thoughts on the beauty in research and its intersections with teaching. This is going to be an interactive session, so we encourage you all to ask questions, preferably by speaking up. So without further ado, let us welcome Professor Howard Stone.
Okay, so thank you all for the chance to visit. Thank you, Afzal, for the invitation. Let me just say what I think I'm going to try and do here. I'm going to first just want to say a few words about myself. I have degrees in chemical engineering. I'm currently in a mechanical and aerospace engineering department, and I find interesting the field of fluid mechanics. I'm going to illustrate that at the very beginning, just so you see some of the things that I get to think about. But I sort of work in the area of fluid mechanics and soft materials, and I will admit that I find problem solving much more interesting than I find any specific problem. And so that sort of has allowed me with my research group to kind of wander a bit around intellectually, which I found very useful. Okay, so here's the invitation I got from Afzal, just so you know that I've sort of created this talk, and I have no idea if what I've created is really going to be useful, but it's what I've done for this opportunity. So Afzal wrote me and said, the topic is supposed to be a bit general and not too technical. And he says, the seminars are slightly different than departmental ones, which are intense and mainly focused on a specific topic. Using a presentation has been a helpful medium, but is not required. I'm going to use a presentation to get across a number of ideas. So if you've, I'm assuming that many people on the call work in some area that relates to mechanics, whether or not you think about yourself as someone in mechanics or not, that's a different issue. But if you did think about yourself in mechanics and you thought about the world, you'd put yourself at the center of the universe and you try and view everyone else as part of that universe. If you don't view yourself as a mechanicist, but view yourself as something else, you'd still put yourself at the middle, and then you'd look around the world and you'd see different things. If you're someone who thinks about fluids and solids, you'd find problems in mathematics, different problems in physics or any area of physics. If it's motion, it could be motion of galaxies. If it's the geosciences, it could be the motion of oceans or atmospheres, planetary interiors, or the image I have to the left, which is a snow avalanche. And of course, if you're in engineering, there are lots of different applications in all areas of engineering that have the mechanics of fluids and or solids in them. And I'm going to show you also an example from biology, but this is just to say that we tend to take our own field, place ourselves in the middle and look at topics outside of that. Then that's fine. I just illustrated it with mechanics, and it is something that I saw a long time ago in a paper by Keith Moffat, who I've acknowledged at the bottom of the slide. Okay, so if you are in fluid mechanics though, and probably also to a good degree solid mechanics, and you ask in the 20th century, who are the people that did the most to illustrate not only the fundamentals of the field, but also the way it can be applied, the way it can be understood, the way it can influence what we do. And I think many people would point to G.I. Taylor and Ludwig Prandtl, two people who you probably run across in your graduate courses and or research, who had a big impact on not only the field as it developed, but even today, the way we look at certain problems and the way we describe certain problems. Okay, so I'm not going to show you a few things from my, either from my research or things I know in the field. There may be 7 slides, I forget. One of the goals is to convince you that nature is elegant and interesting. Another is to show you that patterns can form in many places. Third is to just illustrate one way, one of many ways that fluid mechanics impacts bacteria. And because I'm a fluid mechanician, I'll say that, 18 months ago when the pandemic hit, with some colleagues, I started to think about what would it mean in our everyday life if a virus was airborne, since there was evidence already very early on in the pandemic, though largely either ignored or downplayed, that the virus might be airborne. So there's just some introductory remarks here, and then I'm going to open it up because I have some questions for you. Okay, so if you've never seen me give a talk, or if you have seen me give a talk, you've seen this video. This is a shorebird. It lives in shallow water. It doesn't like to get its head wet. When it's hungry, though, it spins in circles. So for this phalarope, you're allowed to ask the question, why did it evolve this feature to spin in water? And you can think about it. It does it when it's hungry, so it has to do with feeding. And the answer is illustrated by this beautiful image originally taken by a National Geographic photographer who I've acknowledged at the bottom. The spinning of the shorebird creates a vortex. The vortex has with it an upflow, and the upflow carries organic matter and other things that the shorebird might eat to the surface, where it can then peck away at the surface. And I think this is a beautiful example of fluid mechanics, fluid motion, just an amazing feature of what one animal does that involves a fluid flow. Okay, the second I ran across about 5 years ago when in September, right before classes start, I received an email. The email was from the person acknowledged in the upper right, Bob Fankhauser, who I had never met, still have never met him. He described a phenomena of, first show you still images, of pouring coffee into hot milk. Say to make a cafe latte, if you like. And he observed, and we've documented it here in our own images, that in the third image you see that after a few minutes you get these horizontal strata occurring in the hot milk. And he had been asking a number of people where this came from, and eventually ended up writing me an email. Since it was the beginning of the semester, I gave this as a problem to a graduate student who was interested in a project for the semester. And eventually we stumbled on the idea that when you have hot milk, you create horizontal temperature gradients. The pouring process creates mixing, which is creating a vertical density gradient. And what's known in the fluid mechanics literature is that when you have competing gradients that give rise to density variations, you can have fluid mechanical instabilities, which you might be seeing in this video playing on the slide now, where you get horizontal layering. And this was actually already known 90 years ago in the ocean, where it's referred to as double diffusive convection. In many laboratory experiments, it's set up in a very careful manner. These videos show you it doesn't have to be careful. What we did discover, though, is you have to pour fast enough to create enough vertical mixing that you trigger the instability that comes from the competition of density gradients due to temperature and concentration here being the mixing with the coffee. So this was a fun example for us that we then eventually did some numerical simulations and some experiments and tried to make a layered material, but all with the inspiration that this pattern forming system occurs in a very ordinary kitchen setting. And many of you might know that around the kitchen, there's an enormous variety of fluid mechanics problems. So maybe that's something you can maybe even think about for your group at some point for fun. Here's a fluid mechanics problem we stumbled on, and it has since you guys are at the Odin Institute and there's a lot of computational work done, here's a question I then can pose for you. In this experiment, you create a flow over a surface. The little black dots on the surface are a bacterium, Pseudomonas aeruginosa. The black dots are all about a micron in dimension, so about 1/100th of the width of the human hair. And you create a flow in a small channel. You create a flow from top to bottom. And I'll just say that every simulation or mechanical investigation of this kind of problem would tell you that if you create a flow from top to bottom, so you create a shear stress from top to bottom, then objects on the surface should also move from top to bottom because they experience a force. And instead, if you look at what the bacterium does, the bacterium is a living organism that has its own motility mechanism. And what the movie, if anyone wants to speak up, you can. What the movie should be showing you is that the bacteria migrate, but which way do they migrate?
Is it opposite to the direction
Yeah.
of flow?
Yeah, the bacterium, I think you can see are moving opposite the flow direction. And this phenomena is due to the interplay of the bacterium, which is, if you like, an active object, which I could tell you more about, but I don't have in the slide. And the flow. The flow is always trying to move or orient the bacterium. We were the second group to sort of discover this. I put the first reference we're aware of on the slide, but we've studied it in great detail. And one feature that I think is quite interesting is, suppose I give you a network of pipes, a flow network. The flow network, you could imagine, could be your any part of your body where you have blood flow or airflow. It could be a water distribution network. And suppose someone says to you, simulate where the bacteria go. And on the slide, I've sketched arrows that show where the flow is going. If the flow is, say, has a pressure gradient going from left to right. So since you're largely, many of you are computational, you could ask, how would you simulate this? And I will just say that every, and I mean every simulation of any network like this that I'm aware of will tell you that the objects in the flow will follow the stresses in the flow. But these bacterium, as I just showed you, have a propensity for walking upstream. And therefore, in a flow network, in this case, there are two kinds of bacterium, red ones which can't move and black ones which can. What you see is that the black wild type bacterium are capable of moving upstream. And then once they're upstream, if they break loose, they end up in the lower, not the upper channel, even though they're all seated. I'll play it again. They're all seated in the upper channel. And so here's a case where if you, and this is just my way to say, if you blindly simulate systems, but the systems have a little complication that you're not aware of, sometimes you can not just get an answer a little wrong, you can get it very wrong. And it's part of the richness, I think, of this area of so-called complex fluids, where part of the complexity is the richness of the materials in the flow. And so this is an example we stumbled on. And I think and you can then, of course, then go back and realize, how do you make the model better? Well, you need to include something in the model that has the coupling between the motile bacteria and the flow. Okay, finally, I mentioned, in early 2020, the world sort of changed. It changed because of the virus. And already very early on, in February and March 2020, there were newspaper reports suggesting airborne transmission. That's not, wasn't completely accepted. It took the World Health Organization more than a year, I think, to accept that. It was also complicated by the fact that the spreading was partially, if not predominantly, being driven by asymptomatic people. And so in the last 18 months, we've heard about the importance of ventilation. We've heard about the importance of masks. But my group in early 2020, mid 2020, with Manu Kapkarian in Montpellier, France, and a colleague of his, Simone Mendez, started to ask how ordinary speech might be contributing in some way to flows that might carry the virus. And we did some imaging that I show using a high-speed image here, slowed down of a person on the right side speaking, here saying, Peter Piper picked a peck. And what you see in the upper left in the video is the time in milliseconds. So we're not quite at a second yet. The horizontal distance in the image is a meter. And what the high-speed image is sort of showing you is that each time you make a sound that happens to have the P sound, which is referred to as a plosive, you get a small vortex that leaves your mouth. And the vortex is capable of traveling somewhat a distance comparable to a meter in a second. And when you average this kind of speaking pattern over some seconds of speaking, what you get is effectively a conical jet, which looks like what a fluid mechanist person would call a turbulent jet. and that jet easily propagates a meter in a couple seconds if the sounds in it are these plosive sounds. And one reason that you might think this is relevant, whether I'm not sure how many people have paid a lot of attention to it, is that social distancing guidelines are often 1 to 2 meters, depending on where you are, and a few seconds of speech can easily carry material from your mouth to the head of another person. We did numerical simulations. You're a numerical group, so we've done different kinds of numerical simulations inspired by the experiments to look at speaking patterns and how they create flows, and how those flows might interact between a single person just breathing in and out or speaking, or 2 people speaking to one another. And I've just played one of the versions of the numerical simulations we've done that are tied to the Reynolds number of regular speech. And I'll just point out that you can make models of this. I'm not really trying to explain too much, but you can make models for how far your speech goes. Here's capital L as a function of time. And models suggest that the distance that when you continually speak, the distance you contaminate in front of you will change as a square root of time. The parameters here are measurable. V0 is the average speed out your mouth. A is a measure of the size of your mouth when it's open, and alpha is the cone angle of the speaking jet, or so-called turbulent jet. And the graph on the left shows we've done lots of numerics that shows that when you have continuous speaking, it looks a lot like this analytical model where distance goes as square root of t. And we also did experiments to measure the distance versus time in typical speaking patterns. We chose the speaking patterns that have plosive sounds. And on this linear graph of length versus time, all the data points are shown by symbols. The red curve is the square root of t, and the comparison of experiment to simulation is such that the experiments have a slightly different prefactor than the analytical model, and so slightly different prefactor than the simulations. And if you're thinking you're going to go have coffee with a friend, I'll just say to you that if you are a couple meters away from someone and not wearing a mask, you reach that couple meters in some number of seconds. Here for the kind of speaking, we were doing 20 seconds of speaking. And I know for me that in indoor environments, it's one encouragement to always wear a mask when you're with people you don't know. Okay, and finally, Philippe Bourrienne in my group and one of my graduate students, Paul Canila, worked with the Met Orchestra in New York and asked about professional musicians. And here's just a beautiful video if you want to see how fluid mechanical ideas can be combined with cultural activities where the soprano is singing, and we're also imaging where her speech goes with a camera that can image carbon dioxide. And professional opera singers, we believe, actually control the flow rates that they produce. So in some sense, the air propagates less far than you might otherwise think. And I'll just say that some of you mentioned you do image processing. We're not probably as professional as you, but we've done image processing on a wide variety of these flows, both with instruments, musicians, people wearing masks, and many people have demonstrated these ideas qualitatively. We've tried to quantify some of these situations to try to add a degree of quantitative assessment to all of these kind of problems that involve respiration. Okay, so that's my short introduction. And Afzal asked that I try to make this interactive. Yeah, please, who's speaking?
Just one quick question from Mark. So Mark asked, are there any languages that have a less of these explosive sounds and hence less transmission?
Okay, so this is a brilliant question. Mark is right on, I think, in asking it. He's not the first to ask it. Every time I give a talk, it's asked. But I can point you to an interesting story. We're actually trying to address a little of this now using simulation, by the way. something I'm doing with one of my postdocs. But let me just say that if you're interested in this, I don't believe there's an answer, but I think it's interesting to ask. It's interesting to couple it with culture, because in different cultures, people speak at different distances from one another. But in a paper by Bill Ristenpart, I think published in PLOS One about 2019, Bill is a former postdoc, but he was doing all this work on his own. He's a professor at UC Davis. On the last page of his paper, I think the penultimate paragraph, he was studying droplets in speech. And he comments that there was a story in the early 2000s during the SARS-1 epidemic in China. There was a story, and I don't know how, if it's apocryphal or if there's data to support it, but the claim in the paragraph was that there were large groups of tourists in China during the SARS-1 epidemic. There were American tourists and Japanese tourists. And the statement made was that there were many more Japanese tourists than American tourists, but more Americans got sick than the Japanese tourists. So, and the suggestion was that maybe it was something about the languages that were involved in this. So, Mark, I think it's a very interesting question. I don't believe there's any qualitative or quantitative data that I've seen, though I haven't looked at it in detail, but we started to ask, can we use sort of numerical simulations and some other ideas to try to think about this question? And it's a common question that I've heard asked in talks where people talk about respiratory jets and possible links to virus transmission. Did that answer the question for you?
Definitely.
There's
Thanks.
silence. Okay. All right. So I
Can
said,
I ask a question?
Sure.
All right.
This is for you guys. So
Greg, you mentioned music, and a couple of years ago, Metropolitan Opera staged a series of Wagner's operas, and one of them had these three mermaids. And what was absolutely phenomenal is, as they were singing suspended, presumably underwater, they were creating bubbles. And the bubbles really were representing intensity of their voices. Have you seen that? I'm just curious.
No, I
how that
haven't.
was produced.
Well, you're asking the wrong person for that one, but I'll look up the video. But if it's the Metropolitan Orchestra in New York, I'm an email away from at least one of the people who helps run them through these connections they made to visit us during the pandemic, and I could always ask them, but I'd first have to find the video.
It is absolutely, actually, I mean,
okay.
this
Well,
whole staging.
I'm going to do it tonight
phenomenal.
after I get home. So you've really, you've triggered
Sure.
my curiosity.
Yeah, thank you.
Okay. So, one thing we could do now is, I'm curious, I've got a couple questions, but maybe the way to start is, why don't you each think about the following thing? What field do you study? That's presumably an easy question to answer. And what questions do you investigate? You can all think about that. I'm not sure there's, if you want to speak up, you can. Afzal, you can decide how you want to do this. But after you do this, I want you to then think hard about the following thing. What other questions interest you in your field? What are they? And you could ask, have you ever collaborated with anyone outside your research group or outside your research field? That's something I think you can ask yourself. The reason I'm saying that is, I think it's good to ask questions, and you'll be surprised, I think, the more people you talk to, and maybe that's what's so good about the group you have here, is you get to try to find other people who might either share your interests, or you might find questions you can ask that someone can help you with, or vice versa. So I just wanted, I think when I put this slide together, I was thinking people might speak up, but if there are 40 people, I'm not sure how to do that, Afsal.
I mean, if someone would like to speak up, they can just, go ahead and, just introduce yourself and like answer these questions. I think we can pick 2 or 3 people who can, who would want to.
Yeah, it'd be really
volunteer.
nice if someone had an example of a question they're asking that is sort of different than they set out to and was inspired by someone from a different field. That's always fun to hear about.
Gopal, can you hear us?
I'm here trying to think of something. I'll unmute if I do.
All right, well, I have more questions later in the talk, so.
Okay, perfect.
So here's your chance to think about questions that you might not have realized are questions until you start asking. So there's a wonderful quote from Louis Pasteur, who's shown here, that my French friends tells me is better in French, but in English is, in the field of observation, chance only favors the prepared mind. So for me, this is one reason why education's so important. Not because you know answers necessarily, but because when you start to see different things, you might be able to make connections that are important. And so here are 3 examples. I don't know if you know these stories, but the story about Velcro, which many of us have when we have, tying things together or whatever, the claim is that the person, the inventor, recognized the idea when he used to walk his dog across the field, and he kept observing that whenever he walked across the field, these little plant hooks would get stuck in his socks and trousers. And, first it was an annoyance, and then he realized, well, maybe there's an interesting idea here because it's always getting hooked. And so he's the inventor of Velcro, or at least the claim is, because of this serendipitous recognition. Another one you might know is Post-it notes, these notes that aren't very sticky. Is the suggestion is that the scientists at 3M, they were tasked with inventing a strong adhesive. And one day they were very frustrated because they had failed yet again to produce a good adhesive. The adhesive would stick for a little while and then easily come off the surface. And one of the scientists then realized that, well, maybe that's actually good for something. And so the Post-it note was invented. And finally, this sort of traces to the early days of the mid-20th century in New Jersey. The discovery of Teflon, which is now, of course, used in so many surface coatings and pans, was an accidental discovery by a researcher at DuPont. Happened by accident, but then he realized that this material that he had stumbled on actually might be very useful because nothing seemed to stick to it. So there, in all our fields, there are sort of examples like this, and I think they're good to realize, because in your research, sometimes the most interesting things are the things that we uncover that we weren't sort of trying to study. We just realize they're interesting as we're doing our work, and being aware of them is good. And so for me, this moral is always be open to new ideas, and especially when you're talking to people, whether it's numerical or experimental or whatever, that the observations you're making might key new thoughts. Okay, if you want, yeah, somebody?
Professor Beros?
Well, I have a nice historical example. Here's one you're all exposed to in physics, but you might not have been quite taught it this way. But, you know, James Clerk Maxwell, the great Maxwell, you know, formulated what are now known as equations of electromagnetism. And he recognized that in one form, they're a wave equation. And he realized that the wave speed that came from this equation was actually approximately the speed of light. That's because 200 years before Maxwell, there was an approximate measurement made by Ole Romer. And at that time, of course, a conclusion could be drawn, which was that there must be a link between electromagnetism and light. And the conclusion that seemed to then follow was that light was an electromagnetic wave. You can imagine if you try to put yourself back in the days before, we're taught this in school, that making this connection must have been sort of an amazing thing to start to think about. Could this possibly be true? Now, at the time, Heinrich Hertz in Germany then started to study radio waves. And the claim in a talk I heard was that he didn't think, when someone asked, what's this good for? He thought it was just nice, good fundamental research. But of course, we now realize that this changed the world, because now it's everywhere around us, whether it's cell phones or wireless communication or many other things. So what began as just sort of a casual observation eventually evolved to a technology that is now every year leading to new ways we communicate, new ways we calculate, et cetera. So that's maybe something from the history that points out the value of new ideas. Okay, and beauty. So Professor Odin challenged me with a quote from Keats. The quote I know is here on the nature of beauty and research. It's a beautiful quote from Henri Poincaré, and it goes like this. It's given in the language of the day, so I'll just read it to you in the way it's written. The scientist does not study nature because it is useful to do so. He studies it because he takes pleasure in it, and he takes pleasure in it because it is beautiful. If nature were not beautiful, it would not be worth knowing, and life would not be worth living. I am not speaking, of course, of beauty, which strikes the senses, or of the beauty of quality and appearances. What I mean is that more intimate beauty, which comes from the harmonious order of its parts, and which an intelligent person can grasp. So I think for many of us in research and at universities, he's talking about the beauty of intellectual ideas. And a wonderful photograph is shown in the upper right, which of course links Poincaré, here the older scientist to the right, and the great Marie Curie next to him. Now this photograph, which is often shown as part of a larger set of collection of researchers who were present at the first Solvay conference. And in fact, if you look at all of them, it's really a who's who of the history of physics. Einstein is second from the right. Paul Langevin is first from the right. Jean-Baptiste Perrin, who won the Nobel Prize for experiments on Brownian motion, is next to Marie Curie. Lorentz is sitting in the middle of the table. He's, of course, famous from physics, but if you're in low Reynolds number flows, he has a very important theorem in low Reynolds number hydrodynamics, et cetera, et cetera. And of course, among all this group, the only one to win 2 Nobel Prizes is the great Marie Curie. Okay, so for me, what I really find magnificent about this quote is the idea that beauty is about ideas. And with that, then I turn and challenge you to think about the fields you study. And do you want to share, or can you think of an idea that you consider beautiful in your field?
I can share one.
Okay. Who's speaking?
So,
Evan.
So,
okay.
sorry, I should. My name's Evan. For those of you who don't know me, I'm a third-year graduate student in the Odin Institute, and I started my PhD right out of undergrad. And when I entered undergrad, I didn't really know what I wanted to do. And what really convinced me to get into applied mathematics was my first research experience. And my advisor at the time helped develop a connection between PDEs and neural networks. Specifically, he realized that certain types of neural networks could be understood as the discretization of a partial differential equation. And so this isn't obviously maybe a really well-known result outside of the subfield, but I found it really beautiful because it allowed researchers to bring in all these tools from PDE analysis into the neural network, into that understanding neural networks. It sounds
beautiful to me. It really does. That's a great example. Anybody else?
Well, for your information, John Keats died at the age of 25. His most famous poem was Ode to the Grecian Urn. And the last two sentences of that poem are, and I quote, "Beauty is truth, truth beauty. It is all you know on earth and all you need to know."
That's very nice. Thank you.
Well, when I saw the word beautiful, I thought immediately of Keats. That was his debate on what is beauty. Anyway, that's an incidental and not important comment.
Okay. Anyone else?
I have maybe a question.
Yeah.
Nobody wants to chime in. So I think that oftentimes in applied mathematics, we're given models that may be beautiful from people who study physics, biology, etc. And then we're faced with oftentimes the messy task of integrating that with data, with all sorts of complications, constitutive equations, etc., to provide accurate models of the real world. In your perspective, is that something that kind of dilutes the beauty of the purity of, say, Maxwell's equations, or can you find beauty in integrating data and constitutive models into these elegant equations?
So I think that you can find beauty, because at least I'm going to suggest that although there are many problems that are complex, which is very true, there are often underlying features of the problem that help you understand some significant aspect of it using, if you can discover it, simpler versions of the full problem. And then you can start to see from the complexity structure, and I think, if I understand you right, if you can start to recognize what that structure might be, many of us would identify beauty in that, because we start to see how things are connected, even though they seem very complicated. And I believe you can do that often with data. I'm not a data analyst. I tend to look at data that comes from experimental work that we then try to understand, either with, as you said, complicated models, constitutive models, reduced order models. And I'll give an example next. I tend to find problems to be beautiful when one can start to see how to understand them using, if you like, simplified, though still possibly complex models that let you see how different features are related. And I don't see why that wouldn't apply also to problems that are data rich. It might be hard to discover those connections, but that's part of the challenge of finding the beauty.
Thank you for that response. Really like that.
I will actually now maybe give you an example of something in fluid mechanics that I discovered not in graduate school, because no one taught it to me in graduate school, but after graduate school. So in all these things, and I think Evan did a good job of saying why he considered something beautiful. You can then do the next thing is, can you explain intuitively what might be behind the result that you're finding? And if you do that, does it help you understand yet another problem? And so what I'm going to suggest is that in some cases, what we identify, at least in some areas, as beautiful are those concepts that are so robust we can use them many times because they capture ideas for us. And so here's an example from fluid mechanics. It involves what's called plate coating. You pull a plate at speed u out of a liquid, and the liquid has a density and a viscosity. And since these are often small scale systems, there's a surface tension that acts at the boundary between liquid and air or vapor. Gravity acts down to try and keep the fluid interface flat. And your goal as a computational scientist is to predict the film thickness that I've denoted here as H. Now, this problem is associated with two of the great names in physics and physical chemistry, Lev Landau and his student Benjamin Levitch. Levitch eventually immigrated to America, and the Levitch Institute at the City University of New York is named after him. Around the same time, the problem not of a plate, but of a fiber was studied. Fiber coating is actually important today because of so many optical fibers and other things that you need to protect. There, the problem is very similar. Please predict the film thickness H as a function of all the parameters in the problem. Now there's a new one, which is the radius of the fiber. And this problem is associated with Boris Deryagan, who was arguably one of the great physical chemists of the 20th century. Now, these problems have something in common, which is that if you tried to write down a mathematical statement for what controls the film thickness, it would at least involve all the variables that are sketched on the slide: the fluid viscosity, mu, the fluid density, gravity, the surface tension, and the velocity. Now, I'm going to make a few remarks about dimensional analysis later, but you'd probably all know that if you listed 6 variables in a mechanics problem, then because mechanics involves mass, length, and time, there are 3 dimensionless variables needed to describe these problems. And by the way, that's sufficiently large 3 dimensionless variables that that would be a substantial task to numerically investigate this problem thoroughly. But these problems that involve a thin film coating a substrate, be it a planar substrate or a fiber, come up in other problems. So I'm now going to show you 3 more problems that look the same if you look at them a certain way. So one is a bubble in a tube. If you have a bubble moving in a tube, if you tilt your head on the side, there's a thin liquid film that separates the bubble from the tube wall. This problem was first studied by Francis Bretherton, who after studying these kind of small scale problems eventually turned his interest to climate. If you're interested in coating flows in industry, one way they coat systems is they place a big roller in a liquid and they spin it. And you can imagine that here there's a moving boundary. Now it's a rotating boundary, but it drags up a thin liquid film. So these 2 problems both involve a thin liquid film adjacent to a boundary where there's relative fluid motion tangent to the boundary. And finally, if you imagine something like a light bulb or a cylinder, you place a fluid in a cylinder, you spin it rapidly. You can imagine cases where gravity is trying to keep the fluid at the bottom of the cylinder. If you're spinning the cylinder, friction or viscosity is trying to pull the fluid up the side of the cylinder, and you have a plate coating problem. The remarkable thing for me that I only learned as a young professor, I was never taught this, was that all of these problems have the same answer. And the answer is that in a certain limit, which involves 3 dimensionless parameters, but in a certain limit, the Reynolds number is low, so one of the dimensionless parameters go away. And in a certain limit, you only have to consider the thin film as being viscously controlled, and gravity is only important in a static region far away. And in that so-called small bond number limit, there's an asymptotic solution that one can construct, which says that the film thickness H divided by a geometric length scale that changes from problem to problem, and I've denoted it L meniscus, is proportional to the so-called capillary number, which involves the viscosity, the velocity, and surface tension. And this solution is universal. It describes all 5 of the previous problems. And in some of the problems, this meniscus length L is constructed from the density and gravity, in which case you'd end up with a formula that involves all the physical parameters in the problem. And when I stumbled on this, I did not invent it. I sort of read it in a book and then started to realize this problem connected not just the problem, I should say, I read it in a book about these 2 problems. And then I learned that this kind of problem came up in these other problems. And for me, it sort of was transformative. And it's something I've always found very beautiful, which is that this idealized asymptotic problem in the so-called low capillary number limit comes up in many cases in thin films. And once you know to look for it, you find it many places. And not only does it give you then qualitative insight, it gives you quantitative insight. And to go to Evan's question, at least there's lots of experimental data where you can use these kind of laws to understand a problem. And so this is something I've always found in my life, I've always found beautiful. We actually used it to separate a bidispersed suspension by flowing a bubble in a tube. Here you see the bubble moving in a tube. I'll play the video again. There's a bidispersed suspension on one side, but since the film is so thin, only the small particles can get to the back. And so this is an example where we constructed a new kind of problem where we used the bubble and created a filter using the so-called Bretherton or Landau-Levitch-Derjaguin-Bretherton problem. Okay, so what does this have to do with anything? Well, I can't speak for all my colleagues, but I have always sensed that for me, I love the university. I love the concept of a university. I think many people are really excited by research. I think many might find teaching a bit of a distraction. So I just want to challenge that for a second. I realize that there are lots of things that affect American academics, but I will say, for me, I can ask you to think about how might teaching enhance your research. I'm going to ask you that. I'm going to pause in a second. And the reason I say it is, in my case, I will say, and I can provide examples. In my case, I believe that teaching has actually helped me as a researcher over the decades. I think it's enhanced my ability to do research, and it's enhanced it in another way. I'll tell you in a second. But I'm wondering if anyone wants to think about how they might ask, how might teaching enhance your research? And you're allowed to say, although it would be disappointing to say it doesn't, but okay.
Would anyone like to say what they think about the question?
I think it would certainly help with like writing papers and not like, especially to a journal that might not know the notation that you're used to a lot. Learning how to explain that briefly, but not get away from the main purpose of the paper so that your readers aren't lost as well.
Tyler, that's very good. I'm going to say it in a different way in the next bullet, but that's a great point. Just learning how to understand and express yourself in terms of basic concepts in the field.
Adding more to that, I think teaching is a form of self-learning. If I'm teaching a subject to someone else, in a way, I'm learning it, and I'm cementing my ideas. And as Tyler said, it's also communication, which is also a part of the process. So I think teaching means self-learning, which in turns make you more prepared to observe things in the surroundings and make some conclusions.
Anybody else?
Yeah, I suppose I have something. My name is William Barham. I'm also a third-year student at the Odin Institute.
I'm beginning to think that everyone is a third-year student at the Odin Institute. Anyways, that's a joke, but everyone seems to be a third-year student. Okay, go on.
So you, in the previous slide, you were talking about this this universal scaling that was found in these film problems, and I think that sometimes when you're just researching something in isolation, you might be laser beam focused on the various details of your particular problem, but when you're teaching a class, especially if suppose you as a professor had the opportunity to teach a special topics course on your research, you have to present that in a coherent narrative that tells a compelling story from beginning kind of with the first principles of the field and then building it up so that the students might understand it. And so I think that teaching in some ways can help to help a researcher to figure out what is the greater narrative of my research.
I think all of you have said wonderful things. That's a great, William, it's a great remark. And so you guys anticipated some of the things that I'm going to say. I'm going to add one small thing to it. I think you're 100% right. For me, the idea that you learn fundamentals and learn to express them, I think is key. You guys said that. I think you said self-learning. So you have to develop your own way to think about a problem. And I think William sort of touched on this. For me, the other thing that it's allowed, in my case, I can't speak for other people, but in my case, I think it helped me become a more creative researcher, in the sense that early in my career, what I found interesting often about teaching, besides learning, because as I think it was Afzal who said it, and then also just William just now, you got to kind of link things together that was very helpful for you. But I found it really interesting to make up homework problems. I've never been someone who liked to take problems out of books. In fact, I'll occasionally borrow problems, but I like to try to make up problems for homework and exams. And then after you teach for a few years, then you're challenged to make up a new kind of problem so that it's fair to the student, because it's something they might have seen, but it's not identical to something they've actually had before. And so I found this challenge of sort of trying to think about, how do I create questions? How do I create ways to have discussions with students of problems good for my creativity in trying to think about problem solving, ways to ask questions. And in research, you're often trying to ask questions. So I don't know. So this was just my way to say, I think there are links that I found helpful. And I, even on those days where one is pressed with time, I often find it useful to try to just take a step back and try to think about the nice part of teaching, which is I get to try to be creative. I must say it gets harder every year because you think, well, haven't I thought of all the questions I'm capable of thinking of? But then you stumble on something new, or sometimes you read something someone else wrote that gives you an idea. So I think all of you guys, what you said is true. And I just wanted to add this idea that I do think it can help you when it comes to creativity. And to build on one other thing that William said, when you do try to put your own ideas together, what you sometimes discover are research questions people haven't asked, because you've tried to make your own picture of the world you're trying to teach. And then sometimes you'll find little avenues that are worth studying. So I just wanted to say that. I don't know if anyone wants to add anything. Okay, Afzal, I think we're doing okay time-wise. I have one last thing I wanted to talk about, which was dimensional analysis. I'm a big fan of dimensional analysis. Now, one way you use it, of course, is rescaling. You make a problem non-dimensional. Of course, what do dimensionless parameters do? They help you characterize a problem better. I will say, I want to be careful how I say this because there are many wonderful books, but a standard fluid mechanics book teaches dimensional analysis. It teaches it in chapter 6 or 7. If you don't believe me, think of your favorite undergraduate book. In my opinion, that's 5 or 6 chapters too late. But it's the way the mechanical, engineering, and other disciplines teach. And many applied math books touch on this, but many don't. And many papers you read today, you can find that they have dimensional variables all over them. So as one example, not meaning to be critical, but I work in an area called microfluidics, and there are conferences that are referred to as microfluidics. And what I've always found odd about that is it's defining a field by a length scale, a micro scale. But dimensionless parameters don't know about that. Dimensionless parameters are about ratios. And so scale is only part of the problem that comes up. So I've always found it a bit sort of odd that we would have that, but anyways, just my thoughts. Okay, so finally, what you'd read in a book is often encompassed by the so-called Buckingham Pi theorem, which simply says something you've learned, that if you have a problem statement that has n independent, this should say n independent variables and r fundamental dimensions, sorry, I have it wrong here, then the number of dimensionless groups is n minus r. Sorry, this is misstated here. And so that is a good thing. It reduces the complexity in a problem. And in reducing the complexity, you make your life much simpler. Now, I could, challenge you. I assume that everyone on the call, when you study problems, are often making them dimensionless. I would hope that's true, but maybe that's not true. And then we could talk about why that's not the case. But it's true for all kinds of problems, not just fluid mechanics problems and solid mechanics problems. It's true for all math problems, for example. So here's a famous example. You might know this example. If you know this example, then just wait 1 minute and I'm going to tell you something you probably don't know. After World War II, the question about the questions about atomic weapons were raised, and one of them was, what was the energy of the atomic bomb? And here is shown a set of photographs. In the upper right is G.I. Taylor on the right and his assistant to the left. And the story is that Taylor was told by the British government about the atomic bomb. He then was able to make a model that allowed him to deduce the energy of the bomb if he had a little bit more information. For example, the information in a photograph. This idea turned out that a couple other people around the world also recognized. And so the kind of picture that is sort of used to tell this story is an explosion with some energy E in a medium with density rho, and you ask, at least informed by these pictures, which show at different time scales, 0.016 seconds, 0.053 seconds, 0.1 seconds, an expanding spherical cloud, you ask, what's the radius of this expanding shock as a function of time? The story behind this is the energy of the atomic bomb in the United States was a national secret. Taylor had it available to him a set of photographs, which he then plotted as radius versus time, here shown as capital R versus T on a log-log graph. And the line through the data is Taylor's theoretical prediction, and it goes like this. If the model is as simple as the picture on the upper right, then you make a math statement that says the radius little r is some function of the variables in the problem. You want the radius as a function of time. You're told something about a point explosion or a small deposition of energy E in a medium of density rho. The only variables with mass are E and rho, so you can then say that the radius must be some function not only of time, but just of the ratio E over rho. E over rho has units, or dimensions, I should say, length to the fifth divided by time squared. And so the only way you can create a length, which is r, is to write the formula as r to the fifth is some constant c times t squared e over rho, or solving for r, you get this feature that the radius goes as time to the 2/5 power times e over rho to the 1/5. And that's effectively the scales that are shown here. And from this data, Taylor was able to deduce the energy of the atomic bomb, which at the time was a national secret, and there's a small story associated with that. Now, what you might not know is this kind of idea was utilized about 20 years ago. There was a catastrophe in the Netherlands. In May of 2020, a fireworks facility, which happened to be in a populated neighborhood, suffered an explosion. I don't recall all the details, but there was a fire inspection taking place, and this video was then used in the court of law. This video is taken, you see an explosion, and then the camera moves. The camera moves when a shock wave hits the person holding the camera. And so this video has in it information about distance, the expansion of a cloud, and time. Unfortunately, many people died, many were injured. And then there was a court case for what was actually stored in the warehouse where the explosion occurred and who was responsible. And a graduate student, apparently in the Netherlands, realized there was a link of the G.I. Taylor problem to information on the video and made the following graph of distance versus time on a linear graph. The data points come from the video. The curve shown as a red line is the G.I. Taylor formula I showed you on the previous slide. The miracle in the G.I. Taylor calculation is that the prefactor is nearly 1. And from this kind of information video, they were able to get information that gave them an estimate of how much energy was actually stored in the warehouse where an explosion happened. So here's again a serendipitous thing. Someone realized that the video had information, and someone then also realized that, wow, the Taylor calculation gives you a way to learn something about this situation. So that's perhaps a nice example for you. Now, I guess I have a few minutes left, so I just want to then close with, suppose you find dimensional analysis interesting and you want to just learn more about it and learn it as a style of problem solving and as problem thinking. You can probably do no better than this article to start with by Lord Rayleigh, which was published in Nature in either 1914 or 1915. The title of the article is called The Principle of Similitude. And I just want us to read together the very first sentence written 100 years ago. He writes, "I have often been impressed by the scanty attention paid, even by original workers in physics, to the great principle of similitude." And without being argumentative, I just want to suggest that might it be true that even today, many of us work not realizing or not paying sufficient attention to the opportunities available if we think about dimensional analysis. As one example for you, if you want an example for a class or a discussion or one of your meetings over tea, you can just do the following experiment or take a video of a droplet bouncing on a surface. There are 3 snapshots in time shown here. Snapshot A is when the drop first makes contact. Snapshot B is when the drop has spread, exchanging kinetic energy for surface energy. And snapshot C is when the drop has retracted and starts to lift off the surface. If you're interested, I didn't create this. I made up a problem based on this, but it's based on an article that David Curie and colleagues wrote in Nature. And there's a very beautiful result in this, which is that if you measure the contact time of the drop on the surface, which is the graph on the upper right I'm pointing to, it turns out the contact time is independent of the contact velocity or the impact velocity of the drop has with the surface. And because of that, one of the parameters in the problem, the impact speed, doesn't affect the contact time. And therefore, you can then do dimensional analysis to extract the contact time as a function of the drop radius, and you can get all of it by dimensional arguments. So they're nice examples that you can create for classes and for thinking that have physics and fluid mechanics and other things in them. Finally, it's not surprising, and we could talk offline about it. There are lots of examples of this kind of thing. And from a teaching point of view, I've always found them very useful. If you aren't aware of this, there's a beautiful rowing problem that involves dimensional analysis. Many of you, because you're in applied math, study boundary layers. All kind of boundary layers involve dimensional reductions and scaling arguments, if not also a link to a related but different subject, which is the concept of self-similarity, which would also be a topic for a beautiful lecture, I'm sure, if you wanted. And in my view, all of these help enhance your teaching. They enhance your learning, the self-learning that Afzal mentioned, the connections between topics that William mentioned, because they share insights and many ways that topics and ideas are connected. And so I wanted to just remind us of that. Finally, I'll just point out that, Lord Rayleigh was a great scientist. His article got some attention. In fact, the great Darcy Thompson, who's a great scientist of his own, he wrote a beautiful book that many of you might know. He wrote, as shown on the left, I'm not going to read it, a critique of Lord Rayleigh's article. And he actually points out that in the second line, he says, Lord Rayleigh has perhaps forgotten the excellent paragraph in which Tate, another scientist of the age, deals with the question of dimensional analysis and its properties of matter. And then he says, curiously, one of Lord Rayleigh's first illustrations is that of Tate's. Lord Rayleigh responds that he was the one that told Tate about the whole thing. That's the comment on the right. So if you want a little bit of a nice exchange between two great scientists, but also sort of an amusement, I've shared it on this slide. And finally, if you want a really wonderful book, again, an older book that I think is a very nice introduction to dimensional analysis. It's this book by Percy Bridgman, who won the Nobel Prize in Physics for high pressure work. On the other hand, what I didn't know until I was preparing this lecture, or I think I did know and I'd forgotten, was that although I think the Bridgman book is wonderful, there are critiques of it. I won't say I understand the critiques, who point out that they don't think Bridgman has necessarily been true to all the logic of the problem solving. I'll just leave that with you as something to keep in mind if you pull up Bridgman's book. I've always found it useful, and I'm curious in my own self-study to go and try to understand better the criticisms that several people offered, at least in some sections of Bridgman's presentation. Finally, I'll just leave you with one thing that if you've never seen, you may or may not like. I really like, and that is you're introduced to research. Many of us are introduced to research with the idea that they're fundamental ideas in our fields and their applications, and that one is somehow richer than the other. You can choose, but many people in research, I think, would say that fundamentals are dominant. Donald Stokes, a late professor at Princeton, challenged that idea in a beautiful book called Pasteur's Quadrant. Pasteur, who I introduced you to earlier, was one of the great scientists of all time, not only because he studied fundamentals, but he understood how to apply them to real problems. And so Stokes argues that a good way to think about your intellectual work is as a two-dimensional diagram, not a one-dimensional diagram. You should first ask on the horizontal axis, is what you're doing useful? And on the vertical axis, you can ask, is what you're thinking about fundamental? Now, he gives examples of important people who have had great impact on society in the quadrants. For example, in the lower right, he lists Thomas Edison, who didn't really think about why anything worked. He just was this extraordinary inventor. And in the upper left, he gives the wonderful example of Niels Bohr, who didn't worry so much about what anything was useful for, but he did extremely important fundamental work that, of course, has had huge impact on the world. But he saves for the upper right, Louis Pasteur, who worked in both areas. Now, when I give talks to young students, I often suggest that if you had a choice, you can choose wherever you want to be. Obviously, you don't want to be in the lower left. That's not healthy, probably. But being in the upper right is a wonderful goal. Now, maybe it's too hard to get there for most of us, but I do think it's a wonderful goal to have in mind. And so this two-dimensional diagram is something I've always liked. Okay, well, with that, I'll just stop. I put a little summary up there. I hope maybe you found some of this useful. It's not like any other talk I've ever given, and I'm happy to talk to you a bit more. Thank you.
Thank you very much, Professor Stone or Howard. In case someone has a question, please feel free to unmute yourself. Thank you for such a wonderful talk. I'm pretty sure people will have questions. So just go ahead and ask.
Well, Howard, I thought your talk was beautiful. It's a definition of beauty. Thank you.
Thank you for the kind words, and happy holidays, of course.
So while people are thinking, I have 3 questions, Howard, related to your talk. I'll start with one. So first is, I always think about this balance in between knowing and not knowing about a topic, because if I know too much, I build these walls in my mind, which restrict me from pursuing something creative. So I'm curious, what is an ideal approach in your, with your experience?
I'm probably the wrong person to ask. My personality is such that I always feel that others know more, and that many things have been done, and I always have to remind myself to be open-minded. I won't use names, but on 2 different occasions when I was younger, one of my colleagues, when I had almost said the same thing you did to one of my colleagues, he said, I never pay attention to that. I just, encourage myself and my group to work on it, and I worry about all that stuff later. My personality is such that I like reading, I like history, I like understanding, and so I have a hard time neglecting what's been done. I will also say, without using names, that one of my friends once said to me, he said, that's the difference between you and me, Howard. He said, you always think something's been done and everyone understands it. I think people probably did it and they just got it wrong. And so I'll just try and do it right. I mean, I'm paraphrasing what he said to me, but so I like learning, and it probably handicaps me in some ways because I maybe spend a little too much time trying to think about what other people have done and maybe not enough time always doing things on my own. I think it is really great to do things on your own. And as you said, when you're teaching, you get to try to create your own. You sometimes read something and then you have to create your own derivation, your own understanding. But I think there's a tension in that. Does that help a little, Afzal?
Yes, it does. And there's an added question to that. So considering that, papers being written on a topic are increasing, exponentially, they have just exploded, considering, 100 years from now, 100 years ago, there were very less papers being published on few topics. So what's your approach when you read papers? Are you do you read papers which are directly related, or do you also read something, somewhat similar so that you have some ideas, not exactly on that specific approach, but something related with the topic?
Oh, I see. Well, so first of all, when I give advice to young students, especially like summer undergraduates doing research, I actually have a slide that says how to read a paper. And I tell them, read the abstract, read the introduction, read the conclusion, look at the figures and read the captions. And then go back and read the figures and look at the captions, and then go back and do it all again and skip the middle of the paper. First, and then try to figure out what question is the paper asking. I try to encourage them to sort of read it a little qualitatively and not pay attention to too many details to start, because in all our fields, the details are often overwhelming. But first ask yourself, what are the images in the paper? What is the paper trying to do? What question is it trying to ask? Before you go digging into all the details, because it's easy to get lost in all the details. So I don't know if that's helpful, and in my own reading, I like to read papers, and I often read them that way. I try to read the introduction. I try and look at some of the figures. I try and get an idea of what they've done. And, then I pick up another one. And if it's something I'm interested in, of course, then I have to read it in more detail. But I will admit to reading perhaps a bit shallower at first, just for breadth, because I like learning things. And I'm often looking for connections of my interest to other fields.
Thank you. Thank you, Howard. And one last question I have is, as early career researchers or as students, how important it is for us to be focused on our research? Do you think that, should we pursue a research topic from one specific approach, or do you think that we should also learn things surrounding that particular, topic that we are interested in?
I'm not sure I understand the question.
So how focused we should be to our, research topics? Should we increase our domain and, learn things which are not directly related, but somewhat related to our research, or should we only focus on,
well,
things?
Presumably your coursework is meant to give you some breadth, right? But as young researchers, at least the way our system is set up, you have to demonstrate that you have some aptitude and ability for doing research, which means solving something. I think as Tyler or Evan said, you have to write it up. So you have to learn all the steps in research so that you can share it with other people like yourselves all around the world. That's the other wonderful thing about research, right? It's worldwide. It's people from different backgrounds and different cultures. And what you'll all realize this, that some of your best friends in the future will be people you meet once or twice a year who live in other countries, who you just share so much intellectually with. It's one of the beautiful things about the world. But you have to be able to demonstrate some skill in research in order to go on and research the way it's set up. And I think that requires that you pay attention to depth and understanding. Your coursework is meant to give you some breadth. And I think as you then go on in your career, it starts to become easier to add breadth to it. I might worry that if you're too broad and not deep enough when you start, then you won't be able to really dig into a problem in a way that helps you have some progress in your field.
This makes sense. Thank you, Howard.
I had a question, Howard. My experience from teaching is that, dimensional analysis and scaling arguments is something that really seems to divide people, right? There's clearly people that enjoy this, but I just look at the students in class and I see that, some immediately blank out. There's something. Have you experienced that, or is it just my poor ability? But it really, I don't know, some people just don't like dimensionless numbers.
Yeah, so well, not just some people. I mean, lots of researchers, lots of faculty, right? I mean, it's not, I don't think I'm saying anything negative. I'm just saying this is, you only have to look around to realize this. So I don't know. I think it's caring, I think as educators and I think as researchers, we're trying to share understanding. And for me, there's a role for numbers, which is, if you have to design something, then the numbers you choose matter. The material you choose, the thickness of the wall of something, these are real numbers that matter. Now, the design space, you have to think about, you can craft any number of ways. But from the standpoint of understanding, I just have a belief that if what your goal is understanding, then one of our goals as instructors has to be to help people appreciate that dimensionless characterizations help you help you understand problems. Flow in a pipe. It doesn't matter that the speed is a meter per second. You first have to figure out, is there, when you calculate the Reynolds number, is it less than a critical value or greater than a critical value? The absolute numbers on their own don't inform you on the problem. And so one of our challenges is, how do we get that kind of concept across? Because the life, or design or whatever, the understanding of problems isn't about the numbers themselves. And I'll give you an example. All of you know, probably, I might be wrong, but I bet there's a 90% chance I'm right. You take a class in differential equations and you solve problems that have constant coefficient equations, and professor and books, and they all, write, A times Y double prime plus B times Y prime plus C times Y is 0. And then they go through all the trouble of solving all the different cases. But the reality is A, B, and C don't matter. Only some ratio of the parameters matter. There's a dimensionless number that matters. And you eventually say this when you say there's an overdamped system, there's an underdamped system, there's a critically damped system. So it's not about the numbers, but the books, by the way, all teach it about the numbers. But how to emphasize that, I'm not quite sure. I try, I probably like you, I fail. But I think it's an important idea about understanding because, as you know so well, it's sort of the relative things that matter, not each one on their own. And I do think that's an important concept to share and understanding. But you might be right that it's hard for people. I think one reason it's hard for people is the only time they hear it is from the one or two people that teach transport classes, and they don't hear it from anyone else. I'm being recorded.
So I have a memory of, having, this is not...
Yeah, am I being recorded, by the way?
So this is being live streamed. So probably you'll find it on YouTube later.
Well, anyways, but I think yours is the great point, Mark. There's probably no universal answer. I know I've said this among my colleagues. I won't say who. I was challenged by one of my colleagues who didn't think what I was saying was the right way to teach. I disagree with that for the reasons I said. I think numbers and choices are important for design, that's for sure, but understanding and design space requires, I think, that you think about these dimensionless parameters and how we how we teach that and how we illustrate that, I think, is key.
I mean, to me, the key is that it's one of the few ways we have thinking about nonlinear problems, right? And I have a strong memory. The first time I came across that, dimensional analysis, it was, this was already in grad school, and I had taken classes in linear PDEs and things like that. But then I walked into Jack Whitehead. Do you know Jack Whitehead?
Of course.
And
well, not well. He won't recognize me.
Anyway, he's a, I guess, fluid dynamicist, experimentalist for those that. And he just threw this problem at me, and then he just went to the board and said, well, it should just be like this, and it should go like this. And I was like, where does this come from? Right? Like I was sort of the linear PDE trained person, and to me it just seemed like magic. And initially I didn't like it at all, but then eventually it grows on you. And you should probably learn about it before you learn all the other stuff.
But for me, I think the idea is to, for generic problem solving, I think what I often try and remind myself, it's sort of, you're always in getting understanding, it's the relative things that matter. Is something big compared to something or small? What's competing in a complicated problem? Is it possible that in a problem with many variables, only a few of them matter? I think for me, that's where this style of thinking, it might not help you solve the problem in great detail, but I think it helps you think about it and organize your thinking. And I think that's important to share.
This I don't disagree with the question. It just seems that some people really, anyway, this is what I encounter in my classes, that there's some barrier there that's I find surprising.
So one of our goals is, how do we find examples that help people see how this connects to things that they might find interesting or important?
True. Absolutely.
So the one I mentioned about skulls is, because occasionally I would teach and I'd have rowers in class. And so there's this beautiful example about the speed of rowing skulls. And, they're sort of, there's a 1-person one, but there's a 2-person one, a 4-person one, an 8-person one. I think once in history, there was a 16-person one. And so you can ask which goes faster. What's the relationship of speed to the number of people in the boat? Now, of course, this one you can't get by dimensional analysis, but you can get by the extension of it, which is sort of scaling arguments when you think about the relative magnitude of effects. And there's a beautiful scaling law, and it was published in a science paper by Tom McMahon in the 1970s. And anyway, so I think there are examples we can find where we try to illustrate to people how some of these ideas might impact things they do. And in order to think about them, if they want to think about them quantitatively, then these ideas can be important. But again, as you know, they also help you think about things qualitatively in the sense of, if the pipe radius goes up and the density goes down, how does that affect the flow? Is it going to mix as well if it's turbulent or not turbulent? I mean, so there might be things we can do better as instructors for trying to produce sets of examples that help more people appreciate why this might be useful to them, to at least appreciate why we think it's important to think this way.
I think part of the problem is that at least in the geoscience, a lot of students that do modeling or dynamics-based things now work with these extremely complicated models, right? Climate models, climate ocean coupled, ocean ice shelf coupled. And I think it's
well, but that, I mean,
it may be hard for them to see how.
Yeah, no, and their dimensional analysis might not help much, because if you have a problem with 16 variables and you reduce it by 3, it's still a pretty complicated problem. So I'm not saying it's the answer to everything. I am thinking that it can help in many cases, but it's a style of inquiry that I think is valuable. Whether or not enough people think that, I don't know.
Okay, any other last questions?
I also think it's beautiful, but that's okay.
Okay, perfect. I think we can conclude now. It's 3:30 here. So
Yeah,
thank you,
sorry.
Howard.
Sorry I took so long. I realized I went over. I'm sorry.
No, it's good. We started late, so it's not a problem. So thank you very much for taking time to meet and enlighten us on this very important topic. With that, on behalf of Team SIAM at UT Austin, I thank you all for joining us on Zoom as well as on YouTube. We will be back next semester with more events. All the best for your finals and happy holidays. Thank you.
Happy holidays, everyone, and